So we're pretty familiar so far with the concept of an integral representing the area under a curve. We just need to establish the vocabulary of the difference between when they ask for total versus the net area of something. So I'm going to show you this visually first. Let's think about the graph of sine of x. And let's think of that on the interval from 0 to 2 pi. All right, we all know what the graph of sine of x looks like, or we should, on that interval. Okay, and we know that if we set up an integral going from 0 to 2 pi of the sine of x with respect to the x-axis, that the value of that will automatically be what number? 0. Why? Could you, okay, go ahead.
0 to pi is positive and pi to 2 pi is negative.
Okay, so we have symmetry. We've got positive area, which we learned previously has, how much is the value of this region? 2. Okay, we learned that that has a value of 2. And so then by symmetry, we learned that this has a value of -2. Okay, that is called net area. The net value of the two is 0 because the equal section of positive area cancels out the equal section of negative area. To do total, okay, when you switch from net to total, oops, the integral now has an absolute value on it. So it's the absolute value of the sine of x dx. That's the definition of total amount of area. The total amount of area disregards whether it's positive or negative. It just adds it all up no matter what. So visually, the graph now looks like this. The positive section was fine. The negative section is now flipped up above the x-axis. That's what an absolute value does to a graph. It takes whatever was negative and reflects it. And so visually we say, well, it's 2 and positive 2 now. So the value of the integral is now 4, and that's total area. Okay, and we're going from 0 to pi to 2 pi. That's it. That works out really nicely for us because this was a symmetric, we knew the value, everything worked out great. So, but what do you do if it's not a nice symmetric interval like that? And what if it's not a nice shape that you already know the answer of? So that's what we're going to talk about today, is how to handle that from a properties standpoint with the properties that you learned last night. So another way to do this would be to break up the integral into 2 pieces. And so you would have the integral going from 0 to pi of sine x. And then the way to make negative area positive on an integral is to switch the order of the bounds. And so instead of going from 0 to 2 pi, you would switch it and go from 2 pi to pi, and you'd do your bounds backwards. That is the same as achieving an absolute value. That's a calculus way, using the properties of switching the bounds, because switching the bounds is using a negative, and what the negative will do is make that area positive altogether. And so if you have negative area, a quick fix is to flip the bounds and then do the math on that. So let's do a problem that doesn't have nice symmetry like sine. All right, so compare the net and total area for the function x cubed on the interval -1 to 2. All right, so compare the net and the total area. All right, so let's get a visual going of what this cubic looks like. So we know that cubics look like that. Going from A value of -1 to +1 would be symmetric, but then going out to 2 makes it non-symmetric. All right, so that's the visual. The net area is just the straight integral. So my net area would be the integral from -1 to 2 of the function x cubed dx. And I would evaluate that using the antiderivative. I could also shrink my interval, knowing that whatever I do from -1 to 0 is going to cancel out whatever I do from 0 to 1, that those two things are going to cancel out. So I could also just go from 1 to 2, and that would be the exact same value based on the symmetry. You don't have to do that, but you can. So then without a calculator, we would set up 1/4 of x to the 4th plus c, going on the bounds from 1 to 2, and then we would evaluate just like we have been. So 1/4 of 2 to the 4th plus c minus 1/4 of 1 to the 4th plus c. So we're looking at 16 over 4, so that's 4 minus 1/4. So the net area is 15/4. Bless you. To compare that to the total, we need to either use absolute values or manipulate our bounds to take care of the negative sections of area. The total area, I need to break this up from -1 to 0, and I can use the absolute value of x cubed dx and add that to 0 to 2 of the regular x cubed dx. So that's one way to do it. I need the absolute value around the negative part. I don't need the absolute value around the positive part. And to take off those absolute values, I switch the order of the bounds, because that's the same as multiplying by -1, which will make negative area positive. And so you're going to do this total bit in 2 pieces. And so then you'll have the separate integral of 1/4 x to the 4th plus c going from 0 to -1. You'll add to that the integral going from 0 to 2. So then you'll plug in 1/4 of -1 to the 4th plus c minus the 1/4 of the 0. And then the second half of the integral, 1/4 of 2 to the 4th plus c minus the 0 part. Now I'm being very thorough, and I'm showing all of my steps. But I know for sure all the c's will cancel out each other. I also know all the zeros have no value. So -1 to the 4th, that's going to give me a positive 1/4. Plus 4 is all that's left. So I get 17 over 4. The total area should always be bigger than the net area, at least bigger or equal. When would net and total be the same? If all of the area was positive anyway, then net and total will be exactly the same. But if you have any negative area at all, then the net is always going to be less than the total amount. Okay. This idea of breaking up a graph can also apply to a piecewise function. So let's find the total area on -1 to 3 for the piecewise function. So remember, a piecewise function is a bracket, and it's defined as one kind of function all right, one kind of function for a certain domain, and then a different kind of function for the rest of the domain. So this graph is going to be a parabola connected to a square root function. So visually, we have our parabola, which is moved down 1 unit. So there's our parabola. However, our parabola is going to stop at the number 1, so I'm going to erase part of it. My parabola is only going to go up to that much. After that, at that connecting point, it's changing to a square root function, and the square root function is heading out that way. And so I want to find the total area from -1 to 3. Where am I going to break this function up? Okay, well, how's the interval? I'm not going to go straight from -1 to 3. I got to go from -1 up to +1, and then I got to go from 1 to 3 the rest of the way. So I've got area here, which is below the x-axis, from -1 to +1, and then I have positive area out to the number 3. So I'm going to set this integral up from -1 to 1. I'll be using the parabola, x squared minus 1 dx. But I need absolute values around that because it's beneath the x-axis. So I'm going to put the absolute values around the parabola. And then from 1 to 3, and then I'll be using the square root of x minus 1 dx. So again, we remove the absolute values. When we do that, we switch the bounds. So when I drop the absolute values off of the parabola piece, my bounds now have 1 on the bottom with -1 on the top. And I have 2 basically just separate problems to work on in terms of finding the antiderivative. So x squared minus 1 has the antiderivative of 1/3 x cubed minus x plus c. And that's going to go with -1 on the top and 1 on the bottom. And then the antiderivative of the square root. We now have, we should know how to do, remember, square root is x to the half. So the antiderivative x to the half, I'll have x to the 3/2 times 2/3 minus x plus c. And that's going from 1 to 3. And then you're going to evaluate each of those. So I'll have 1/3 times -1 to the 3rd minus parentheses -1 plus c, that's the negative plugged in, minus 1/3 of +1 cubed minus 1 plus c, which means I'll distribute my negative all through that. And then I'll also have 2/3 of 3 to the 3/2 minus 3 plus c minus 2/3 of 1 to the 3/2 minus 1 plus c. So be careful that you don't rush there. All the c's are going to cancel each other out, but make sure you're distributing the rest of your negatives correctly so that you're not dropping terms. So I feel okay that I can do this, okay, and getting rid of all my c's. So I will have 1/3 times -1 cubed is -1/3. Minus a -1 is +1. Then I'm going to have minus 1/3 again, and then a plus 1. So that's the first half where I've distributed my negative sign back. Then the next half, I'm going to have 2/3 of the square root of 27, which is 3 rad 3. So 2/3 times 3 rad 3 minus 3. And then my negative here needs to distribute. So I'll have negative 2/3 times the cube root of 1, which is 1, plus 1. So we're going to put all of that together. I have negative 2/3 at the beginning when I take the two negative 1/3 put them together, and then plus a 2, and then reduce. So I'll have 2 rad 3 minus a 2 and minus a 2/3. So I just kind of like to sort of group all my things together here, because then it's easy for me to see that I've got a plus 2 and a minus 2, which will cancel each other out. And then I have 2 negative 2/3, so I have negative 4/3 plus 2 rad 3. That'll be a positive number, because the total area's got to be positive. That's probably as simple as you need to make it. I mean, if you really wanted to get a common denominator, you could say negative 4 plus 6 rad 3 over 3, but I think either way is probably fine.